In this 3D particle equilibrium problem, we want to determine for static equilibrium what is the tension in the wires AB, AC, and AD. We don't need to find AE because, again, AE is directly attached to a weight, so we automatically will know what the tension in that is while we're in static equilibrium. So we want to find the tension in TAB, TAC, and TAD. And we are given that the weight of this crate is 150 pounds. All right, so we're going to need, since we're in equilibrium, we are definitely going to need a free body diagram for this. So let's start by drawing our free body diagram. Now we need to establish what is our object or our particle of interest. Well, we want to know what's happening in AB, AC, and AD. Point A is common to all three of them, so point A is going to be a good place to make our particle. And I'm going to keep the coordinate system that was given to us and base all of my coordinates off of that. Right, so the origin is not at A, it's back here, and this is my x-axis. Okay, so A is the particle. I'm going to be seeing all the things that are affecting it, and A is going to have cables running from A to D, A to C, A to B, and I have the weight of that crate. So let me start putting the forces that act on point A. So right away, straight down in the negative Z direction, I have my 150-pound crate. So the weight from that pulling down. Also, I'll have the tension in cable AD. It's directed along AD, which goes in the positive X direction. So I know right away that TAD is acting along that positive X direction. Now I have cables going from A to B and A to C. So I do want to put these points here because I know that if I have a cable going from A to C and A to B, that the force is directed along that cable. So here's my point B out here and C over here. So pointing from A to C, I will have TAC, and pointing from A to B, TAB. I'm in 3 dimensions, so putting down coordinates is going to be really helpful here. So I want the coordinates of A and B and C. The origin is at 0, 0, 0, so that's okay. D is going to turn out not to matter because I already know that TAD is pointed along that positive X direction. So let's put the rest of these coordinates. So A is going to be at 6, 0, 0 feet. B is going to be, it's on the the ZY plane, so it's 0 in the X direction. I have to go 3 in the Y, and I have to go 2 in the Z. And C also is in the ZY plane or YZ plane, so 0. In the Y direction, -2, and in the Z direction, +3 feet. And I want all these coordinates because I'm going to need to use them to find position vectors, which I'm going to need to use for the unit vectors when we get to the equations part in a second. Right, so I now have my complete free body diagram. I have all the forces acting on point A, and I have enough information to be able to find the direction of these forces. So we can start on our equation step. Now, before we really do anything with the equilibrium equations, I want to find TAC, TAB, TAD. I want to find their components. It's going to make it much easier for this next step. So that means I need to find the directions of all of them. AD will be easy. Actually, I can, right away, I know that vector TAD is just TAD, and it's in the I hat direction only. So I don't need to, I can find the unit vector, but I know it's I hat. The others are not going to be quite as simple. For those, I do need to find U hat AB, U hat AC, and I'll need to use position vectors to do so. All right, so let's start with U hat AB, since just go in alphabetical order here. So I know that it is RAB over the magnitude of RAB, which I can write like that. Right, so RAB is going to be the end point minus the start point, so B minus A for each of my components. So it's going to be 0 minus 6 is negative 6i, 3 minus 0 is plus 3j, and 2 minus 0 is plus 2k. And I need to divide by its magnitude. That's going to be 6 squared is 36, plus 9 plus 4 is 49, and the square root of that is 7. So this one, the numbers worked out nicely so that I have nice round numbers or nice fractions to use. So that's 6/7 I plus 3/7 j plus 2/7 k. That is the unit vector going from A to B. Which means I can write TAB, I'll usually skip this step, but I'll write it out here, is going to be TAB times U hat AB, which I just found, which is going to be then negative 6/7 TABI plus 3/7 TABJ plus 2/7 TABK. All right, so I'll write out the longhand here. I will start to skip this step pretty soon when I go to my equilibrium equations. All right, and I need a C because I also need to be able to write TAC in its component form, basically the same way I just did it here. So TAC is going to be RAC over its magnitude. All right, so C minus A is going to be 0 minus 6 is negative 6i. Negative 2 minus 0 is minus 2j. And 3 minus 0 is positive 3k. This actually has the exact same magnitude as AB, RAB, which is convenient. So I can write this as negative 6/7 I minus 2/7 j plus 3/7 k. And I don't have to write TAC out explicitly. We're going to see with the equilibrium equations that we can automatically be picking that out. All right, so equation 1. Let's start writing our sum of forces equations. So I'll start in the x direction. Now, I will let the free body diagram guide me, but since I already know the components of all of my forces, or I can figure them out very easily, it's going to be pretty quick to write these. I just need to pick out the I components of every force, of all 4 forces. All right, so I have all of TAD is in the positive x-axis. I have AB, just the I component, is going to be this negative 6/7 TAB. Notice I'm not writing I's, J's, and K's because I'm only writing the coefficients from the I's, the J's, or the K's for each of these equations, minus 6/7 TAC. So I didn't write out explicitly TAC as a vector, but I know it's going to be whatever the I component of the unit vector is times the unknown magnitude. And then my weight does not act in the x direction. So in equation 1, I have 3 unknowns, TAD, TAB, TAC. Not much I can do with that at the moment. 3 unknowns, 1 equation. All right, so let's go and write some more equations until we have something solvable. So let's look in the y direction. AD only had an I component, so nothing to write there. I have 3/7 TAB minus 2/7 TAC. And the weight, again, is only in the z direction. So here, not much I can really do. I have 2 unknowns in this, and I have a total of 3 unknowns and 2 equations. So I can write my last equation, the z equation. Again, TAD does not appear. I will have 2/7 TAB. Make sure it's AB. And plus 3/7 TAC. And I want to remember the weight is completely in the negative z direction, so minus 150 pounds. All right, so I have, at this point, 3 equations and I have 3 unknowns. I have a solvable system. If I were going to solve this by hand, I could take equations 2 and 3 and I could at least have only two equations for the same two unknowns and solve it that way. However, again, I'll do this in Mathematica, and I'll be able to solve it more quickly. Okay, so I can use my solve for these three equations. So I have TAD minus 6/7 TAB minus a 6/7 TAC, and that is equal to 0. And 0 is also equal to, I'll do this with a list of equations. I'll do it a little bit differently. And equation 2, 0 is 3/7 TAB minus 2/7 TAC. And equation 3, 0 is equal to 2/7 TAB plus 3/7 TAC minus 150. All right, so I have the list of three equations. They're in those curly braces because it's a list of three equations. I'm using the double equals here because that's how I set an equation, an equality, not an assignment. All right, so this should work. Okay, so it's giving to me as fractions. Probably I don't really want in this case, my answer in fractions. So I want it as 3 digits of precision for my answer. All right, so it tells me that TAB is 162 pounds. And it's positive, so that's tension, which it needs to be. TAC is going to be 242 pounds, also in tension. And we find TAD is that 346 pounds. So we have the tension in those three ropes that we solved simultaneously with the three equilibrium equations that we developed. So again, if we inspect what we did here, it was a 3D problem. Putting down those coordinates is a really good idea to get everything started. We needed to know the direction or the unit vector for every one of our forces. Now the 150 pounds by inspection we knew was in the negative z. That one we didn't need to go through a lot of work. We just knew that. TAD was directed along the positive x-axis, so we knew that that was only in the I direction. So as AB and AC, we found their unit vectors. You had AB, you had AC, and that lets us split up the components of AB and AC. So TAB I did write out the long way, where I do multiply my unknown magnitude by my now known direction to get its components. And AC, I just wrote the unit vector. I didn't go through that extra step because I know when I write my equilibrium equations that I, at that point, am doing that multiplication. Right? So we saw that the I component was negative 6/7, so that appeared with TAC in equation 1, the negative 2/7 with TAC in equation 2, and the positive 3/7 with TAC in equation 3. And we put those three equations together for our three unknowns, solved for the three tensions, noted they were all positive, and they have to be because they must be in tension for this problem.